All right, so I'll go ahead and start talking here. Looks like we just hit 110. Hope everyone's doing all right. If you don't mind, I think it'd be great if you turn your cameras on. I just think it creates like a little more uh, kind of nice environment, a little more communal experience. Hi, Luke. Hi, Usman. Yes, there we go. Lucas is there. I see you. Harry, hi. Okay, so obviously some strange times here at Reed and on planet Earth, but we're going to keep doing some learning, so that's nice. I wanted to just kind of open things up for questions initially. You know, I sent out an email where I tried to describe how we'd use Zoom and how we'd use Gradescope, and of course the extension on homework. Um, any questions about all of that stuff? If you have one, unmute yourself or start waving vigorously, and I'll unmute you. Pretty simple. Okay. All right. Well, we're gonna struggle through this together. I'm learning a lot. I already did Math 113, and so you will benefit from the mistakes that I made there. Hopefully, I won't replicate them. But we are gonna just jump in, and I'm gonna kind of lecture, and I've got some visuals, and I'll share my screen, and that'll happen. If at any point you have a question about what's going on, you have two options. You can either, and this is preferred, just unmute yourself and break in and say, hey, just a second, how does that work? Or there's a chat button down at the bottom of your screen probably, and you can send a chat out either just to me or to the whole group. There's a slight risk that I won't notice the chat notification and I'll miss that. So that's why I prefer breaking in, but either way should work. All right, so I am gonna start sharing my screen here, and in particular, I'm gonna bring up this one here. So can everyone see my bad tablet handwriting? Great, okay. So this is where we are. We're talking about pencils of geodesics. We started this last time, and we got just to the cusp of proving the reflection axiom. But before we do that, I wanted to review a little bit of this stuff and take a look at it again. So remember, we're working in little SL2R, right? And these are our trace 0 2x2 matrices. So those look like A, B, C, and minus A, right? And this has a symmetric bilinear form on it, where we say that the inner product of A and B is, I've totally forgotten the sign, I believe it's -1/2 times the trace of A times B, right? And this was jerry-rigged so that when we take the norm of a vector, whoops, we get its determinant. So we're looking at that inner product space. And this, of course, is a Minkowski space, three-dimensional. Okay, so we then have our preferred hyperbolic plane. And that's going to be the matrices that look like A, B, C minus A, right? And that have A squared plus BC equal to -1. So that would be the hyperboloid. And then to specify our sheet, we'll take C bigger than 0. Okay, so that's our model, and we know in this model that we have geodesics, right? So those geodesics can always be parametrized so that they look like gamma, right? And this is, sorry, equals A times hyperbolic cosine of t plus t times hyperbolic sine of t. And here A is in H and T is in the tangent space at a 2h, so that just means the space of vectors that are orthogonal, right? That is equal to a perp, and it also has norm minus 1. Okay, so those are those, and we figured out that these have, obviously this point that they pass through at time 0, that's a, right? And then they have t, right, which is we interpret as a tangent vector, right? So a is gamma of 0, and it's a simple computation to see that t is gamma prime at 0. And then our big definition, I guess, was that we also had a normal vector, which was given by taking the wedge product of t and a. So of course that looked like this kind of, I was going to say Lie bracket, which is accurate, but anyway, it's this operation where we take 1/2 of t times a minus a times t. And in general, that will be perpendicular to a and t, and it will have norm minus 1. So before I move on to the reflection axiom, I actually want to show you what that looks like. And I spent an inordinate amount of time making this, this picture. So let me switch my sharing screen here to Chrome. And here on our course website, if you go to today's meeting, Monday, and you click on this geodesics SAGE worksheet, then you will get this business here. And it is unfortunately the case that this particular method of sharing in CoCalc doesn't render the 3D images, but if you click the green button, then we'll get a new window. This is going to take a little while, but it will actually pull up the proper, oh, is it going to go? Should show up soon. All right, sorry, this is taking just a little while. I want to go there. I don't know if you're doing this at home. It may have pulled up faster for you. So I'll just start describing what is going to appear here in the hopefully soon future. What I've done is I've actually plotted the hyperbolic plane. Here we go. And so this is the picture down here. And to explain what's going on, we've got this blue sheet here, and that is H inside of SL2R. Now, how am I graphing inside of SL2R? All I'm doing, like we have those A, B, and C coordinates in the matrix. So those are our X, Y, and Z axes here. So this is just that the sheet cut out by the equation for the hyperbolic plane, and there it is. And what I've done with these green lines is just chosen some more or less arbitrary initial points A and tangent vectors T. So let's focus on this one first. And what you can see here is that one of these red arrows is pointing from the origin to the curve. That arrow is A, right? That is a point that the green curve is passing through. And then we also have a tangent direction. I thought about labeling these, but you can actually see it from context, right? So at that, I just pointed with my finger. That's not going to work. At this point right here, there's a clear tangent direction, right? And this red vector over here is indeed the tangent vector for this. Now, what is this gray sheet? Here with the gray, I'm plotting the vectors of norm minus 1. Okay, so that's that sort of shape like this that appears in the standard model of the hyperbolic space, Minkowski space. So good, that's on that sheet. And then the normal vector is the third red line there, which I computed just by taking the wedge. So then we can look at this other geodesic. And again, this blue arrow is A, this blue arrow is T, and this one back here is the normal vector. You know, that's how it works when we actually picture everything in inside of this three-dimensional space. We can also draw some little cartoons in a model of H to look at these. So I'll do that in a second. But I just wanted to kind of scroll up. This is well, you now know that I'm not a programmer. I consider this a moderate amount of code to have written. Yeah, I mean, there's just a little bit going on here. You know, we're doing some parametric plotting of some curves. I'm telling it the initial data, A and T, and then more or less just doing the parameterization that I wrote down. And then I've also defined an auxiliary function which takes the wedge product of two things. So you can go in and look at that in case it's something you want to play around with. I do think it would be pretty cool if you had a system where it was interactive and you could, you know, sort of move A around and then move T around and then have it generate the associated geodesic and normal vector. But I didn't get around to that. And I think that would be substantially more work on the programming end. All right, so any questions on just AT and geodesics, that stuff? All right, looks good then. Let me come back. Oh, how do I do this? Right. Okay, so we're back here. And I'm sharing my handwriting again. In terms of, you know, just cute pictures of this, right? I mean, okay, if we're in the upper half plane, then we've got a geodesic. It looks something like that, goodness. And, you know, here is our point A, right? And then it's got a tangent direction. So something like this. All right. And, you know, the normal, I'm going to draw it like a Euclidean normal. It's not, but we can kind of loosely think of it that way in our heads. Cool. Do notice that if we were in the plane, right, the Euclidean plane, and doing this, right, then, all right, I'm in the plane and I've got a line, right, and that has a point it goes through. It has a tangent direction, and from those I can determine a normal direction. So it's all in analogy with that type of picture. Okay, so that's that. Now let's get to this reflection axiom. So that's theorem 17.1 in the notes. And this says that if we look at a geodesic L, and then we look at its complement inside of the hyperbolic plane, this has two components, connected components. Okay, and reflection tau, and by this I mean reflection in the normal vector or along the normal vector n for L, that will fix L pointwise. And moreover, interchanges the two connected components. Okay, so let's sketch the proof of that. I'm going to do most of it live here. It's all written in the course notes. What I'll omit here, I'm going to show that there are at least two connected components. I'm going to omit the proof that each connected component is in fact connected. I'll make some comments on how you prove that. But what we can begin by doing is looking at a function from H to R that takes some vector and spits out the inner product of that vector with the normal for this geodesic. So it's not hard to see that this is equal to 0 if we're on the geodesic, right? Because the normal vector is perpendicular to the geodesic, okay? And it is non-zero on the complement, because in fact the normal vector determines which geodesic we're going through. So we have a set U, which is the set of elements of the hyperbolic plane where this function takes a positive value, and we have V, the same thing, but where it takes a negative value. Right, and the claim here is that these separate the complement. Okay, so I mean, there's a little topology going on here. Hopefully it feels like a familiar statement that if I have a continuous function and I look at open sets in the codomain and I take their pre-image, that those are going to be open sets. So if you were taking a point set topology class, that would actually be the definition of being a continuous function. But in this case, I mean, these are Euclidean in the, well, the weak sense. These are both R3 mapping to R, and you should have seen in vector calculus that if you have a continuous function, the preimage of open is open, or at least that the preimage of an open ball is open. So hopefully that's believable. That we have these two open sets. They're disjoint by definition, and so we know we're going to break H minus L into at least two pieces. Now let's look at the reflection part. I think I need to make a new page here. Cool. So for the reflection, so let's let tau be reflection in the normal vector. Then we can write down a formula for this. Tau of x is equal to x plus twice xn. And this is our normal reflection formula when n is a vector of norm minus 1. And from this, we can easily compute that if I have the inner product of x with n, it compares quite nicely to the inner product of tau of x with n, right? So I would just plug this formula in, and we would learn that one is the negative of the other, right? So that tells us that this function, sorry, so the tau interchanges both u and v. Okay, so what's left is to show that u is connected. Okay, I mean, this is a reflection, so it's, if you compose it with itself, you're going to get the identity. So as long as u is connected, we know u and v are homeomorphic, and that would finish the proof. The idea for this, I'll let you read it in the notes, but the idea is to take A and B, both belonging to U, and just connect them with a geodesic. We have a lot of control over those, and we can verify that that geodesic will stay inside of U. And that's then enough to show connectedness, shows path connectedness, in fact. Okay, so questions on that proof? Again, just unmute yourself. I've got like 2 monitors set up here, and you're all on the monitor over this way. So when I'm like looking off to the side, it's because I'm looking at you. Okay. Oh, yeah, someone?
Yeah. Did the you said that thing about the pre-images being open. Is that, are those I guess inner product is continuous, right? Or
Yeah,
the
yeah,
form is continuous. Okay.
yep. Yeah, we do need that continuity, but that's pretty standard. Okay, anything else? All right. In that case, oh, let me find myself here. Cool. Let's. I'm just going to talk a little bit. I mean, there's a lot written down in the course notes. We've got now sides of a geodesic, right? So if you have an oriented geodesic, then it has a tangent vector. And you can say, well, if I've got some other vector in the hyperbolic plane, what's its inner product with the normal vector, right? When you take t wedge a. And it's either going to be positive or negative. It's either going to be in U or in V. And we call, when it's positive, we call that the negative side. And when it's negative, we call it the positive side of the geodesic. So that's just a funny bit of terminology. Cool. So what else can we do now? We can also look at angles in the hyperbolic plane. So let me write a little bit about that. Angles. Cool. All right. I need to turn off my notifications. How do I do that? Down here. Oh, do not disturb. Okay, I don't know how to turn off notifications. Someone can tell me later. All right, so angles. Let's do it. So the so here's the idea of what I want to do, right? I want to have a couple of geodesics, right? And this is going to be some sort of agnostic hyperbolic plane here. I don't know what model I'm working in, but those are supposed to be geodesics. And they intersect somewhere, right? And if these will then have tangent vectors, right? So we're going to have a tangent vector here, call it S, and we're going to have a tangent vector. Ooh, that's bad. Try again. Whoops. We're going to have a tangent vector over here, call it T. Okay, and what we're going to define here is that the oriented angle between S and T living in the tangent space to some A. So the idea here is that this point of intersection is our A. This is given by the following formula, namely that T can be expressed in terms of S and the cosine of this angle. So I'm going to write angle sub or for oriented angle between S and T, plus S wedge A times sine of the oriented angle between S and T. Okay, and remember that, you know, S wedge A is going to be a normal vector, right, for this other curve. So S wedge A is somehow this vector. And we're just more or less kind of doing that circle parametrization of these vectors all tangent at A. So it's a plane, and they're unit tangent vectors. I guess I should have written that. This is all for S comma t, unit tangent vectors. Okay, so then we can talk now about the intersection of geodesics in this language. So if we've got geodesics L and M, and let's suppose they're oriented, so maybe L is going this way and maybe M is going this way, and they pass through this common point A. Cool. Let's let U be the tangent vector to L. So there's U. And let's let V be the tangent vector to M. So here's our V. These are unit tangent vectors. And let's then define the directional angle from L to M. We'll define that to be, we'll call it alpha, and it is the oriented angle from V to minus U. Okay, so you know, you got to be a little careful with all these signs and whatnot, but you end up with the relations ultimately just working with this equation up here that defined an oriented angle, right? We know that minus U will equal this cosine and sine combination of V and V wedge A. And so when we plug that in, we learn that the inner product of U and V is equal to the cosine of alpha. So that is probably a familiar formula with inner products. And we also learned that when we take, oh, sorry, that's a typo. Yeah, oh, sorry, okay. I'll erase this. I didn't mean U and V there. I forgot that I need to define H to be U wedge A and K to be V wedge A, right? So these are these sort of SL2R versions of the cross product. And when we do that, the correct formulas are that the inner product of those normal vectors gives us cosine of alpha, and the wedge product of H and K gives us A times sine of alpha. Okay, so in particular, if that's going to hold, then this inner product had better be strictly less than 1. And that's actually exactly what verifies that two geodesics intersect in the hyperbolic plane. So proposition, distinct geodesics L and M intersect in H if and only if they're normal vectors that was my 3-year-old whose fever is much better. If and only if they're normal vectors satisfy that their inner product is less than 1 in magnitude. So this is nice. We have this like very effective test for whether these geodesics are going to cross. I mean, maybe we can do that visually, but if they're given to us in a more abstract way, we'll care about a test like this. And the proof here, we're going to have a whole fleet of propositions. They're going to have similar sorts of statements. I'm going to sketch the proof of this one, and the proofs of the other ones are very similar in nature. So in the course notes, I pointed you where to read those in Iverson. I didn't think it was going to be particularly beneficial to rehearse them in detail. But this one, I'll go through a little bit. So the proof. So we already did one direction, right? We already saw that when they intersect, the magnitude will be of the inner product of normals will be less than 1. For the other one, let's suppose that this quantity is less than 1. And then let's look at the discriminant of the plane that they span. So that's span of h comma k. I'll call that E. And this discriminant is, now we're going way back to all that chapter 1 stuff we learned about. And it is, this is why we did all of it. It's this. Okay, but let's do the computation here, right? These are normal vectors, so they have norm -1, and -1 times -1 will be 1. And then I'm subtracting off this thing squared, but our hypothesis here is that that quantity is going to be less than 1. And so overall, this discriminant is positive. Okay, and so what we call the discriminant lemma, then tells us that E has a particular Sylvester type, namely -2, 0. Okay, how does that help us? Well, it allows us to compute the Sylvester type of the orthogonal space of E, right? And that is necessarily going to be type 0, 1. Okay, and now, gosh, where are we here, right? We're in SL2R, and I'm taking this plane E, and then I'm taking a normal to it, and it has type 0, 1. That normal with type 0, 1 necessarily intersects the hyperbolic plane. And where does it do so? In the point of intersection of the geodesics. Okay, so again, just to kind of recapitulate what happened here, we started off with geodesics. We didn't really know where they were. We took their normal vectors, right? Those determine the geodesics. And we said, well, let's look for stuff that's mutually orthogonal to both geodesics. And we found such a point that was on the hyperbolic plane. And so that has to be the point where those things intersect.
Oh, why does the thing with type 0, 1 half intersect?
The thing with type 0, 1 is necessarily going to take a positive value.
Oh, so it can be scaled to be.
And then you can scale it to have norm 1. Yeah.
Okay.
Good question. Anyone else? Okay. So this proof, I mean, I think it gives us like an insight to what other kind of behavior we can expect out of geodesics, right? Well, this inner product of normal vectors can be equal to 1 in magnitude, or it can be greater than 1. And so those are the other two cases. Sorry, I lost track of where I am here. So this is the question we're trying to answer now. What about having inner product of magnitude 1, or having inner product of magnitude, greater than 1? Okay, it turns out one of these is easier to answer than the other. When they're greater than 1, these are just parallel geodesics. But I'll put a modifier here with no common end. Okay, so what's going on here? I mean, obviously, I just said that they intersect if and only if the norm is less than 1. So I could have an easy statement here that when the norm is greater than or equal to 1 in magnitude, then they're parallel. But there's kind of an edge case that I want to distinguish, which is this idea of having a common end. So here are some geodesics that are parallel in the upper half plane model. Oh, great, those didn't intersect, right? So this would be the greater than 1 case. Here are some geodesics that also don't intersect in the hyperbolic plane. So remember that when you're in the upper half plane, this boundary, the actual real axis, is not part of H, right? That stuff is the, those are the lines in the isotropic cone, right? This boundary of the hyperbolic plane. And so right here is this phenomenon of what we're calling a common end. Okay, and this is when what happens when the inner product has magnitude 1. Okay, so I think I might even just like forego the formal statements of all of that written down. They're in the course notes, and I can't write as fast electronically as I can on the chalkboard. But does everyone get the flavor of what's going on here? These three cases intersecting, kind of genuinely parallel, very parallel, and then parallel with a common end. Okay, great. That brings us then to the definition of a pencil. Okay, so so what is a pencil? It's a set P, script P, which I'll write as a set of L, where L is a geodesic in the hyperbolic plane with a normal vector P. And here, of course, P is a fixed element of SL2R, trace zero matrices with norm -1. Okay, so what are the things that all share a normal vector? No, I totally botched that. That doesn't make any sense. The normal vector determines the geodesic. P is not an element of SL2R. Sorry. P whew, is a fixed plane. Ugh. In SL2R. Okay, so fixed with normal vector, I meant to write in P up here. Okay, so is that, sorry, I just made a total misstatement there, but we've got a plane fixed in SL2R, and we're saying, what are the lines, the geodesics, whose normal vectors live in that plane? Okay, and the discussion above actually tells us nearly an answer, basically an answer to that question. So I have a claim to make. Yeah.
Question. When you say plane, is that affine or linear?
Yeah, I'm talking about a linear plane, so plane through the origin. So here, my claim is that P is spanned by its vectors of norm -1. Okay. Visually, this is really clear. I mean, if you think about that shape that's built by the norm -1 vectors, right, then any plane is going to have a spanning set that, you know, lives on the norm -1 gadget. So I'll let you think about a formal proof if you want to. But then that tells us that P, whoops, this plane is the span of normal vectors of geodesics in the pencil. Okay, so in that way, you know, a pencil is a set of geodesics determined by a plane, but then, you know, we also know that the plane is determined by the geodesics, so we can go back and forth. P is going to have one of 3 Sylvester types. Namely, it could be Sylvester type -2, it could be Sylvester type -1, 1, or it could be Sylvester type -1, 0. And the conclusion in the first case is that P perp has type, this is the proof that we did before, type 0, 1. And so P perp intersected with H is a single point A. And the pencil here is geodesics through that point A. Okay, so that's one type of pencil. The second case leads to geodesics perpendicular to a fixed geodesic. And the third case leads to geodesics with a common end. Okay, and if you had gone through the proofs of those other, what's the norm of the inner product of the normal vectors, those would be relatively clear statements. I'll just sketch some quick pictures. So we have a geometric feeling for what these 3 types are. I'll do them in order. So we could have a point A and then a bunch of geodesics through it, right? We'd have this whole family that I'm not drawing very nicely, but you get the idea. Okay, so that's one case. Another case is that we've got some fixed geodesic L, right? And then we're going to look for all of the geodesics that are perpendicular to L, right? So here's another one that I can draw, right? And I can just keep going like that with all these things perpendicular to L. And then the last case is that I've got a common end. So then there's my end, and I just have this whole family of geodesics like so. Okay, so those are our three types of pencils, and they're all determined by the Sylvester type of the plane, the fixed plane. Okay, so I think the last thing is just a sort of omnibus proposition with a few properties of the hyperbolic plane. I'll send you to Iverson for the full proofs. I also encourage you just to think about them in, say, the upper half or Poincare disk model to make sure that they make sense to you as statements. So we've already formally proven this one in any model of the hyperbolic plane, namely through two distinct points, A and B. There's a unique geodesic through those points. That's our incidence axiom. Secondly, given something in the hyperbolic plane and a geodesic L, there's a unique geodesic that goes through A and which is perpendicular to L. Okay, I'm trying to think if I need a hypothesis there. I think, no, I don't need any other hypotheses. Hopefully you're sketching a picture of that right now while I talk. And then the third one of 5 is given some point A in the hyperbolic plane and an end. So there we mean something that's on the boundary of H. S, then there's a unique geodesic through A with end S. Every geodesic has 2 ends. S will be one of them. Next page here. Okay, so part D. So now we've got an end S and a geodesic L with ends different from S. Then there exists a unique geodesic perpendicular to L with end S. So that one's maybe worth drawing. That's getting a little weird, right? We've got this geodesic L, we've got some S over here, and we're claiming that there is, in fact, that's supposed to be a right angle, a geodesic that goes, has S as its end and is perpendicular to L. And then finally, part E, their given ends are in S, distinct ends. There exists a unique geodesic with those ends. Okay, that may be the most obvious of all of them. We'll stop there today. That's Pencils of Geodesics, and we'll pick up again on Wednesday. So I will first off, any questions right now?
Why are they called pencils?
I do not know what the etymology of that is. That's a little bizarre, isn't it? I'll get back to you if I find something. Okay, I'll stick around here if you have a question that you want to ask me in an after class sort of format. I'm here. I'll also be on office hours in just a moment. That's in a different Zoom room. But yeah, if you want to just stick around, I'm here for a moment. But otherwise, I will see all of you on Wednesday, and stay healthy.